So welcome back. Today we want to look at the chi-square test of independence. So we normally use this test when you want to test if there's some association between two variables where you assume one is dependent on the other, or if they're independent, or if one is independent of the other. So we're going to use today our fictitious data set right here to explain, which looks at different delivery methods for a curriculum. So you had different methods. You had blended, face-to-face, and you had online. And you also had the different outcomes for example, a test was done after the curriculum or the course or whatever was delivered, and you had pass or fail. And here we have sex, where you had the different persons were represented, whether male or female. So for example, now we want to find out if the outcome of passing or failing was dependent on the delivery method, or if it was independent of the delivery method. Then we can use the chi-square test of independence. So let's learn a little bit about that test. So in the chi-square test of independence, the null hypothesis is that the row and the column variables are independent, and we'll discuss later on what are row and column variables. And the alternate hypothesis would be that the row and column variables are dependent on each other. So just remember, the null is that they are independent. The alternate is that they are dependent. The requirements, so again, if you are making inference about a population from a sample, ensure that it's randomly selected. The sample data should represent frequency counts in a two-way table, meaning the table should display the interaction between the variables, between two variables. And every cell in the contingency table should have an expected frequency of at least 5. And I want you to remember that this test is a non-parametric test. As you see, there is no requirement for normal distribution. Now let's return to our data set. So here in our data set, let's see if the outcome of passing or failing was dependent on the delivery method. So we'll go to analyze. So when you come to analyze for the test of independence, it's important to know you're not going down to non-parametric and chi-squared, because this will take you to the test interface that we use for goodness of fit, but we're not doing goodness of fit, we are doing test of independence, and we want to use a cross tabulation to develop that table. So we'll go to descriptives, cross tabs. So I'm repeating that again for you in case you miss it. You go to analyze, you go to descriptives, and you go to cross tabs. So normally when I'm doing this, the independent variable, or the variable, the variable, I don't want to really use the word independent to confuse you, right? But the independent variable, I would normally want to put that as the row variable. So the test outcome, I would put that as a column, because that is the dependent. And here in the row, I'll put the one that we assume is independent in the row. So what we do next, so we'll look at these different interfaces here. So here you have format. You could just leave this as is. Statistics. You see a lot of different tests that you could perform using the cross tabulation. I will discuss some of them in other videos, but it will automatically check for the Pearson's chi-square. And here, so you also see it mentions different tests like Fisher's exact test and so on. So you leave that check because we want to do a chi-square. Click continue in your cells. So we want to know the count in each cell. And remember, the cell is where the both variables interact, or the values in each variable interact. We want to look at the row percentage, the column percentage, total percentage, and it's good to check as well expected. Sometimes the expected might be unchecked, but ensure you check it, because we want to ensure that each cell has a value of 5 or more. Then you click continue and you click OK. So here we get our output. Our output is telling us that we have 280 cases in this data set. And here we have a lot of different things that could confuse you a bit. But if you look at the count, what this count here is saying, I'll just show you how to interpret it. it's saying that 37 persons that fail had face-to-face delivery. This is saying 56 persons who pass had face-to-face. Okay? And if you look at this one here that's saying 86, it's saying this 86, you had 86 persons who passed and they had a blended delivery. That's what it's saying. However, when you're interpreting now the row percent and the column percent, you have to be a little bit more careful. So in the row percent, you're reading across the row, as it suggests, row percent. So let's look at face-to-face. So this row percent here is saying 39.8% of those who had face-to-face failed. This here is saying 60.2% of those who had face-to-face pass. If we look at blended row percent, it's saying here that 8.5% of those who had blended fail. And this here is saying 91.5% of those who had blending pass. And that is how you interpret it. And for the column percent, if we look here, for the column percent here where it says 45.1% of those who fail had face-to-face. And then we come down further and look here where it says another 45.1% of those who fail had online. And when you look here at this column percent here, it says 9.8% of those who fail had blended. And if you consider pass, you look here, it's saying 91.5% of those who pass were blended. And if you look right here where it says 28.3% of those who pass had face-to-face. And I just want to come back here just to point out something. I made an error. It's 43%. You're looking at the column percent, right? For this column. So it's 43.4% of those who pass had blended. So you could normally look at the numbers here and you could pick up a trend to see if there's some dependence or independence that you could actually comment on. But before we interpret this output, I want to point out something. So if you look at the expected frequencies here, you look at these values, you can see that these values in these cells, they are greater than 5. So we did not violate that assumption. But for example, if you had one of the cells or a couple of the cells that their frequencies were less than 5, two strategies could be employed. The first one is that you try to group some of the values in a variable as much as possible. And that could help to bring up the expected frequencies. If not possible, or if you're still having issues, you could break the table down to a 2x2 table where you have two values for both variables. And then you could use and you get an output for Fisher's exact test. So because this one had two values for test outcome and 3 for delivery method, you wouldn't see the Fisher exact test statistic come up here. But if it was a 2x2 table, you would see that Fisher exact 2 test. And even if you still have a frequency count of a cell that's less than 5, that test, the Fisher exact test, compensates for that. And you could use the p-value from that test to make a decision. However, here we see that all the assumptions were met, so we have no violation. And if we look here where it says Pearson chi-square, so we see we have a large chi-square value, which would tell us that more than likely we'll have a small p-value. And here the p-value is showing that it's less than our standard alpha of 0.05. This would tell us that we reject the null hypothesis. And if you remember clearly, the null hypothesis states that the variables are independent. So therefore, we have to assume that because we reject that null hypothesis, we have to assume that test outcome appears to be dependent on the delivery method. And as I'm saying, if you look here at the row percent here, we could even see that blended seem to have a special effect because 91.5% of those who had blended actually pass. And when we consider all those who pass, blended had the highest rate. So blended at 43.4, while online at 28.3, and same did face-to-face. So that is how you perform the chi-square test of independence using PSPP.